Last time we looked at the law of sines and saw how the identity that the law of sines states can be used to solve triangles that are not right triangles, that have angles other than 90 degrees in them. What we saw is that for various combinations of pieces of data about the triangle, we could use the law of sines in a couple of different ways to find the other pieces. We always needed 3 pieces of information, including the length of at least one of the sides. However, there were some combinations of angle measurements and side measurements where knowing them couldn't tell you the rest of the values just using the law of sines. For this, we need to use the law of cosines. So we use the law of cosines to solve triangles when the known information is in the pattern side angle side or side side side, meaning that we are going to use the law of sines when we want to solve a triangle where we know the lengths of 2 sides of the triangle and the measure of the angle between them, or when we just know the lengths of the 3 sides of the triangle. Neither one of these situations allow us to use the law of sines because in these situations we don't have information about an angle and a side opposite to work with, which is what's necessary to use the law of sines. So to get at the law of cosines, let's look at a triangle and see what we might be able to do with it. Let's suppose that we've got a situation like this, where we've got an angle alpha, side A on the opposite side, an angle beta, side B, and an angle gamma and side length C. And furthermore, I want to go ahead and put this on a coordinate grid. I want to imagine this as actually sitting inside the Cartesian plane because we're going to use some of the relations between the trigonometric functions and points in the plane. So when we do this, we can label the various points on the triangle. This point has coordinates c, 0. This point has coordinates 0, 0. This point up here we don't know yet. I'm just going to go ahead and label that point k, h. And in fact, I'm going to draw in another line that comes down like this, and this point down here has coordinates k, 0. And what we're going to do is take this figure here and use what we know about trigonometric functions and the distance formula to find a way of relating things together. Now, we're imagining that we're in a situation where we know, for instance, B, alpha, and C, but we don't know A, beta, or gamma. So we're going to try to express A in terms of alpha, beta, and gamma. So that's our goal. To express A in terms of alpha, B, and C. I think I might have said alpha, beta, and gamma before, but we want to express it in terms of A, B, and C. Once we have A, once we figure out what A is, then we'll be able to use the law of sines, because then we'll know the value of A, we'll be able to know the value of alpha, and we'll know B and C. And so from there we'll be able to get beta and gamma. So let's look at a few things. I want to combine a few different formulas together. So first of all, I want to look at sine and cosine of alpha. And I'm going to do that by looking at the right triangle with alpha as one of the angles and with the green segment as its opposite side. Now the green segment, of course, has length h. So we can say that sine of alpha is equal to h over b. That's just opposite over hypotenuse for the triangle, for the right triangle with angle A alpha. Cosine alpha is k over b because the length of the segment that goes from the point 0, 0 to k0 is k. And now we also have the distance formula. We have that A is equal to, well, it's the distance between the point C, 0 and the point K, H. And so that gives us that A is the square root of K minus C squared plus H minus 0 squared. And this I want to rearrange, and I want to express these things in terms of sine alpha, cosine alpha, and b. So from here we get that a squared is equal to k minus c squared plus, well, h squared. Now h and k can be expressed using the two trig functions equations that we came up with before. We have that h is equal to b times sine alpha and k is equal to b times cosine alpha. So that means that we could write this as a squared equals, now instead of k we can write b times cosine alpha squared. Instead of h we can write, forgot to subtract c, minus c squared. And then h is b times sine alpha squared. So let's expand all this out and see what we get. If we FOIL out the top, or the first term here, we'll get b squared cosine squared alpha minus 2bc cosine alpha plus c squared plus b squared sine squared alpha. That's what we get when we expand all that term out. Now you'll notice that we have two terms here that each have a b squared as part of them, and they're multiplied by a sine squared and a cosine squared. If we gather those up, that means that we could write this as b squared times cosine squared alpha plus sine squared alpha plus c squared minus 2bc times cosine alpha. Well, that gives us that a squared is equal to, now cosine alpha plus cosine squared alpha plus sine squared alpha is 1. So this first part is just b squared times 1, so we just get b squared plus c squared minus 2bc times cosine alpha. And so this gives us the formula for the law of cosines, which I'll write down in just a second on the next page. But this is how we derive the formula that we're about to use, and it allows us to find a when all we know are the other two sides of the triangle and the angle opposite it. This is also going to allow us to find or to solve triangles where all we know are the three sides, because if we know A, B, and C, we can use this in order to find alpha. So, the law of cosines. Given triangle ABC labeled in the standard way, we have that a squared is equal to b squared plus c squared minus 2bc times cosine alpha. Now, of course, we can also write down this same equation with uh, the other angles and sides involved. So when we look at this pattern, the thing that we notice is that the side length sitting on the left side of this equation is the one opposite the angle that goes inside the cosine. So following the same pattern, we have that b squared is equal to a squared plus c squared minus 2ac times cosine beta. And we have that c squared is equal to a squared plus b squared minus 2ab times cosine of gamma. All three of these equations are the law of cosines, and we can use it to relate any of the angles with their opposite sides and the two sides adjacent to the angle. All right, so we'll look at some examples of how we use this in a second, but first I want to talk about some general strategy for using the law of cosines. So we only use the law of cosines if the law of sines won't work. The law of sines is typically easier to use, and so if the law of sines will work to solve a problem, go ahead and use that. It's typically much faster, much more efficient to use. When you use the law of sines, on a triangle with side, side, side given information. That is, if the problem gives you just the three sides of the triangle and no angles, solve for the largest angle first. And then, finally, use the law. And then once you've used the law of cosines once, use the law of sines for the rest. Once you've used the law of cosines once, you will either know one more side or one angle that you didn't before, at which point you will be able to use the law of sines. So you should, except for very strange situations where you've got multiple triangles you're working with, only use the law of cosines once on any given triangle that you are trying to solve. All right, let's look at an example. Solve triangle ABC if alpha equals 56 degrees, B equals 17, and C equals 6. So, as normal, you will want to sketch out this triangle in order to organize your information. And you've got the angle alpha, which you're told is 56 degrees. And now B and C are the two sides on either side of the angle alpha that are adjacent to it. And so in particular, we are not given any information that we can use the law of sines on. We don't have any angle and opposite side, so law of sines won't work. Also, we're only given the one angle rather than two, and so we're not going to be able to figure out the other one just by subtracting them from 180 degrees. This is precisely the sort of situation where we would use the law of cosines. So let's see how this goes. In the law of cosines, we want to choose the version of the law of cosines where the angle in the cosine, in the formula we use, is our known angle in situations like this where we know one angle and two sides. So we're going to want to use the version of the law of cosines that involves alpha. So that's going to be a squared equals b squared plus c squared minus 2bc times cosine of alpha. So let's see how that goes. A, we don't know. That's what we're going to be solving for. So a squared is equal to 17 squared plus 6 squared minus 2 times 17 times 6 times cosine of 56 degrees. And so that's a great big expression that you will just plug into a calculator. So let's do that. We get that a squared is equal to, and we've got 17 squared plus 6 squared minus 2 times 17 times 6 times cosine of 56. I double check that I'm in degree mode, and that gives me that a squared is equal to 210.9246 to a sufficient number of decimal places for what the problem's asking for. And so then a will be the square root of this. Of course, we don't have to worry about the any positives or negatives here because a is a side length of a triangle. It's always going to be positive. So that means to find a, we'll just take the square root of 210.9246 and get that a is 14.523. And I'll leave it there. So a is 14.523. And there we go. And again, we want to make sure that the numbers that we get here are of the appropriate scale, or of the same sort of scale as the rest of the problem, rest of the numbers in the problem. And getting a number that is between the other two side lengths is a good indication that you're in the right ballpark. Though, of course, it can be greater or lower than them also. All right, so that's great. We used the law of sines and we worked out one of our unknown quantities. Now from here we need to move on. Now we know all three sides and one angle inside. At this point we can use the law of sines. Now another piece of information or another trick that we can use here when using the law of sines at this stage, you want to solve for the smallest angle since it is always acute. What that means is that we're never going to have any sort of ambiguity with that one. You'll remember that when we were working with the law of sines, sometimes we got a situation where we had to break our problem up into a couple of different cases because we had more than one possible solution. The smallest angle in a triangle always has to be acute. It's in fact, the two smallest angles in a triangle always have to be acute. And so when you are at this point, you know the lengths of all three sides, which means that you know which one of the angles is smallest. You can always go for that one because only one answer will ever be correct on that. You will only ever get an acute angle out of that. So in our case, we see that the shortest side of the triangle is the side C with length 6. So let's solve for that one. So using the law of sines, we have that sine of gamma over, sorry, I wrote under my calculator there. So, law of sine says that sine of gamma over c is going to be equal to, now we'll use the angle and side length that we actually know. At this point, unfortunately, we are forced to use some quantities that we already evaluated, already deduced as part of the problem. We're going to be using A to figure out gamma here, but there's unfortunately nothing to be done about that. When we are going to be using the law of cosines on a problem, we are typically going to have to be using the values that we compute from it to compute other ones. So this means that sine of gamma over 6 is going to be sine of 56 degrees over 14.523. And so from here we can get that sine of gamma is equal to 6 times sine of 56 degrees over 14.523. Let's go ahead and work that out. We'll have 6 times sine of 56 degrees divided by 14.523. And that'll give us that sine of gamma is equal to 0.3425. So from here, to figure out what gamma is, we'll have that gamma is equal to the inverse sine of 0.3425. And therefore, we get that gamma is 20.03 degrees. And again, because that's opposite the shortest side of the triangle, it's the smallest angle, and therefore it must be acute. We don't have to consider the other angle that has this sine value. So we're almost done with the problem. The last thing to do is to figure out what beta is. This is straightforward because now we have two of the angles in the problem. We just need to say, well, beta is 180 degrees minus 56 degrees minus 20.03 degrees. And that's going to give us 180 minus 56 minus 20.03, which gives us 103.97. And so you see that here's the advantage that we got from going for gamma first rather than beta. Beta, in fact, is obtuse, which means that if we tried solving for beta first using the law of sines, then we'd actually have the two different possibilities. We wouldn't know which one was which, and so we'd have to continue on and try and arrive at a contradiction for one of them. So by starting with the smallest the smallest angle in the triangle and solving for that, you eliminate those possibilities. In fact, in this sort of pattern where you're given a side angle side pattern of data, there's never going to be any sort of ambiguous solutions. You're always going to get exactly one solution out of that, which is pretty nice. Okay, let's look at how we use the law of cosines when all we're given is information about the side lengths. So let's solve triangle ABC if A equals 6, B equals 10, and C equals 11. So in this case, we're going to start by solving for one of the angles. Start by solving for alpha, beta, or gamma. Let's see, let's label this as A equals 6, B equals 10, C equals 11, and then we've got alpha, beta, and gamma, all unknown. Now, there is a good strategy to use here. When applying the law of cosines, in the case side, 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 we always want to solve for the largest angle first. I mentioned that earlier. Now, the largest angle is always opposite the largest side. The largest side of this triangle is side C with length 11. Therefore, we're going to start off by solving for the angle gamma. So we want our law of cosines that involves a cosine gamma here. We know that gamma inside the cosine goes with a c squared on the other side of the equation, and then it's the other two side lengths that go into the formula. So the law of cosines with gamma says that c squared is equal to a squared plus b squared minus 2ab times cosine gamma. So working this out, we have 11 squared is equal to 6 squared plus 10 squared minus 2 times 10 times 6. I guess I wrote those backwards, but of course it doesn't matter, times cosine of gamma. And now at this point, we need to solve for gamma. Doing that, we get that cosine of gamma, 11 squared minus 6 squared minus 10 squared over negative 2 times 10 times 6, which we'll plug this into the calculator and get 11 squared minus 6 squared minus 10 squared, all over negative 2 times 10 times 6, and we get 0.125 out of that. Now, notice that because we've got these negatives running around, it's entirely possible for you to get a negative number out of this computation for various values of a, b, and c. And that's all right. That means that your angle gamma is simply an obtuse angle. It's got an angle measure of more than 90 degrees, whereas when your cosine of gamma is positive, that just means that gamma has an angle measure of less than 90 degrees. So getting negative values out of this is all right. On a related note, the fact that we're using cosines here has the nice advantage that we only have to compute one thing here. If cosine of gamma is equal to 0.125, then gamma is simply equal to inverse cosine of 0.125. We don't need multiple angles the way that we did with sine. And that's because we needed multiple angles when we were doing the law of sines, because sine is positive in both quadrant 1 and quadrant 2, both for angles less than 90 degrees and between 90 and 180. And so knowing that sine of an angle equaled some number couldn't distinguish between an angle in quadrant 1 and quadrant 2. Cosine can, because cosine is positive in quadrant 1 and negative in quadrant 2. Therefore, cosine can distinguish between those two angles, and so we only ever need to do one computation at this step in the problem. And in fact, we can simply say we want the inverse cosine of 0.125 and get that gamma is 82.819. I'll go ahead and round that to 2 decimal places here. So we have that gamma is 82.82 degrees. And so that's great. That means that we are well on our way. We now want to figure out the angles alpha and beta. And we'll get one of them using the law of sines. Now, at this point, it really doesn't matter which one of them you figure out. Because we solved for the largest angle first, it's guaranteed that the other two angles are both acute. And so when we go to solve them using the inverse sine function, we know we just take the value that the calculator gives us for the inverse sine. So let's go ahead and solve for alpha. So using the law of sines, we have that sine alpha over A is equal to sine gamma over C. We can do this now because now we know gamma and C. And so rearranging, we'll have that sine of alpha is equal to A times sine of gamma over C. I'm just going to go ahead and plug in those numbers right now. We have that sine of alpha is 6 times sine of gamma, which we know is 82.82 degrees, and then C is 11. So we get that sine of alpha is equal to, sorry, I lost my calculator. Sine of alpha is equal to 6 times sine of 82.82 degrees divided by 11, and we get that sine of alpha is 0.5412. So that's going to tell us that alpha is equal to inverse sine of 0.5412, which in the calculator again gives us inverse sine of 0.5412, and we get 32.77 degrees. So alpha is 32.77 degrees. And then finally we can figure out what beta is by subtracting alpha and gamma from 180 degrees. So beta will be 180 degrees minus the 32.77 degrees that alpha is, minus the 82.82 degrees that gamma is, and so beta will be equal to 180 minus 32.77 minus 82.82. And so beta will be 64.41 degrees. Now's a good time to go back and check and make sure that all of your angle and side measurements make sense, that your largest angles are opposite your largest sides, your smallest angles are opposite your smallest sides, and that all of the numbers involved are reasonable. That is, if you have an extreme difference in side lengths, that should have a corresponding extreme difference in angle measures. In this case, everything makes sense. The largest angles are opposite the largest size. All of the side lengths are in the same ballpark with each other. And all the angle measures are not too extreme. So everything looks good here. And in fact, we've solved our problem. Now, in the case that the data that you're given is of the pattern side, 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 that is, you're given the 3 side lengths of a triangle, it can be the case that you have a set of data that doesn't correspond to a triangle. That is, it is possible to have no solution to a situation like that. Let's see an example and see how we would recognize that. Let's solve triangle ABC if A equals 2, B equals 5, and C equals 8. So, once again, we're going to try to solve for one of our angles. Again, the best practice is to solve for the largest angle in the triangle, and the largest angle is going to be opposite the largest side, so it'll be gamma. So the version of the law of cosines we want to use is c squared equals a squared plus b squared minus 2ab times cosine gamma. Now plugging in all of our known information, that gives us that 8 squared is equal to 2 squared plus 5 squared minus 2 times 5 times cosine gamma. Now, if we solve for cosine gamma here, we get that cosine gamma is equal to 8 squared minus 2 squared minus 5 squared over negative 2 times 2 times 5. And this one we can actually do by hand. This is 64 minus 4 minus 25 over negative 20. 64 minus 4 is 60. 60 minus 25 is 35. So we get negative 35 over 20. So we get the cosine of gamma is equal to, if we reduce that, we get negative 7/4. Now, as I mentioned on the previous problem, having a negative value here isn't a problem. A negative value of cosine simply means that the angle involved is greater than 90 degrees. It's between 90 and 180 degrees. The bigger problem here is that this value of negative 7/4 is less than negative 1. This is less than negative 1. And cosine of gamma will never equal a number that's less than negative 1. And so this equation here has no solution. And that doesn't just mean that the law of cosines failed to solve this problem. That means that this problem has no solution. So this means that there exists no triangle with these three side lengths. So that's how we can detect it if we try to solve a triangle given three side lengths. This is how we'll detect that there's no solution. When we try to use the law of cosines, we'll wind up with cosine of some angle being greater than 1 or less than negative 1. All right, now there's another application that the law of cosines has that winds up being very useful and convenient way to calculate the area of a triangle. We know that the area of a triangle is given by 1/2 base times height, but a lot of times we're in situations where we know two side lengths and the angle between them. Well, we can use the diagram that we did out at the very beginning of this video in order to get an expression for that. So let's I want to just copy this and get a new page here, and I want to ask what is the area of the triangle? Well, of course, we know it's 1/2 base times height. And there are a number of ways of measuring that, but you'll notice we already have a height of the triangle that's been laid out. So let's go ahead and use that. We know that the area of the triangle is going to be 1/2. Now the base of this triangle is C, the way that we've drawn it out here, and the height would be H. But the height here can be expressed a different way. We also know that the sine of alpha is equal to H over B, which implies that the height of the triangle is equal to B times sine alpha, as we've got it set up this way. So this means that the area of the triangle is 1/2 times C times B sine alpha, or if we rewrite it in the more standard way, we get 1/2 BC sine alpha. This turns out to be, as I said, quite useful, because if we want to find the area of any triangle at all, and let's say we know that this side has length 2, this side has length 7, we know there's a 33-degree angle inside, we know that the area of this triangle is simply 1/2 times 2 times 7 times sine of 33 degrees, which is a much more convenient way of solving it than trying to work out directly what the heights of this triangle or anything are. So, in this situation, we can quickly figure out that the area is 0.5. Whoops, that was 0.05. So 0.5, 1/2, times 2, times 7, times sine of 33 degrees. The area of this triangle is 3.812 square units, whatever the units are in the context of this problem. Now, it turns out that we can also use the law of cosines to figure out the area of a triangle, or to get an expression for the area of a triangle simply in terms of its side lengths. Now, I'm not going to go through the derivation of it here because it's a little tedious, but it is in the book, and I recommend reading through that and seeing how we apply the law of cosines in order to get there. Now, this formula that we're about to have has a name attached to it. This is Heron's formula. Given a triangle with side lengths A, B, and C, the area is the square root of s times s minus a times s minus b times s minus c, where s is 1/2 times a plus b plus c. This formula here gives us a convenient way of figuring out the area of a triangle, specifically when we're only given the side lengths. So let's see an example. Let's find the area of the triangle with side lengths 2, 3, and 4. So when using Heron's formula, usually the first thing you want to do is just compute s here. Compute this number s. So s is going to be 1/2 times 2 plus 3 plus 4. 2 plus 3 plus 4 is 9, so s is 9/2. So that means that the area of this triangle will be the square root of 9/2 times 9/2 minus 2 times 9/2 minus 3 times 9/2 minus 4, which gives us the square root of 9/2 times 9/2 minus 2 would be 5/2, 9/2 minus 3 would be 3/2, and 9/2 minus 4 would be 1/2. So we wind up with the square root of 9 times 5 is 45. 45 times 3 is 135. I shouldn't be doing this, though. I'm going to want to simplify this, and so I'll keep the 9 separate. So I'll take 9 times 15 over 16. And now all the things in there that are perfect squares can be simplified. So we get 3 times the square root of 15 over 4. Now, of course, in most applications, you'll simply have numbers that are approximations to begin with, and so you'll just plug this into a calculator. But it is interesting that we can find the side lengths of this, or the area rather, of this triangle via a pretty quick formula just based on the side lengths. As an interesting side note, let's look at what happens if we try to find the area of a triangle that doesn't exist. So let's try to find the area of the triangle with a equals 2, b equals 5, and c equals 8, the same triangle that we looked at before. Actually, I'm going to adjust this slightly in order to make some of the computations a little bit easier. We'll get a equals 2, b equals 4, c equals 8. Don't worry, turns out this triangle still doesn't exist. So if we want to use Heron's formula, we'll need to calculate this number s. It's 1/2 times a plus b plus c. So we get 1/2 times 2 plus 4 is 6 plus 8 is 14. So s is 7. And so then the area of the triangle, we know there isn't a triangle with these 3 side lengths, would be 7 times 7 minus 2 times 7 minus 4 times 7 minus 8. And that'll give us 7 times 5 times 3 times -1, which gives us the square root of, well, it doesn't matter a whole lot. It's -105. The reason it doesn't matter a whole lot is because there's that negative in there, which is going to make the whole product negative. And of course, the square root of a negative number isn't defined. And so this would be another way of detecting when if the side lengths or potential side lengths don't actually make a triangle. If they did make a triangle, you'd be able to know its area using Heron's formula. If Heron's formula gives you a number that's not a positive real number, then those side lengths don't correspond to side lengths of any triangle.